Good morning, class. We are looking at chapter 2, limits, and here's 2.3, limits of functions at finite numbers. We covered limits of sequences, limits of functions at infinity, and now limits of functions at finite numbers. And here's the definition of a limit, one-sided limit. We discuss it with more details. Here's the summary of what we covered. Limits of sequences, the summary is a sequence is an ordered list of numbers or function f whose domain is the set of natural numbers 1, 2, 3 to infinity. Limit refers to the long-term behavior of a sequence, i.e. what happens to a sub n of a sequence in the long run. The limit of a sub n as n approaches infinity is L. We say that a sub n converges to L. If this limit is infinity or negative infinity or D and E does not exist, we say the sequence diverges. To find limits, simply plug in the value and observe. These are a couple of theorems we discussed. The limit of 1 over n to the power of p as n approaches infinity is 0 for p larger than 0. Meaning, when the denominator gets larger and larger, a fraction gets closer and closer to 0. The limit of r to the power of n as n approaches infinity depends on the value of r. If the base is somewhere between -1 and 1, the answer is 0. If it's 1, it's 1. And if it's larger than 1, it becomes infinity. Geometric sequence. When we multiply by a common ratio r, we add them up, becomes a series, and it has the solution a times 1 minus r to the power of n over 1 minus r. If we take the limit of this expression as n approaches infinity and r is somewhere between -1 according to this theorem, this part goes to 0. And therefore the answer becomes a over 1 minus r. B sub n plus 1 is r b sub n. That's the recursive solution. And b sub n is b sub 0 r to the power of n, where b sub 0 in some cases, in some texts, they call it a. That's the general solution. Explicit solution. And if we add a constant, like giving medication to patients at a specific time step, then this formula insists, and then we add plus c times 1 minus r to the power of n over 1 minus r because of the 1 minus r because of the constant, and remember a or b sub 0. Finally, we looked at the horizontal asymptote, or short HA, of the curve y equals f of x is y equals L. If the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches positive infinity is L, in that case, y equals L is the equation of a horizontal asymptote. Now, section 2.3, limits of functions at finite numbers. Finding limits by numerical and graphical methods. Definition. Limit of f of x as x approaches a equals L. The limit of f of x as x approaches a equals L. That's how we read this expression. Let's look at all these graphs. There's a slight difference in all of them. As x approaches a, here's a along the x-axis, here's the left side, we are in this part of the graph. From the right side, we are in this part. And we are approaching this point on the graph which has the y coordinate L from the bottom and the top. And if you look at all these three cases, approaching A from the left and right, they in all cases end up having this point as the limit to the y coordinate of this point. So in all of them, the limit of f of x as x approaches A is the same thing L. What's the difference? In this case, f of A is also L. There is no discontinuity. So the limit and the functional value are the same. So the function is continuous. In this case, f of A, there's a hole here, there's a solid point here. F of A is the y coordinate of the solid point B. And in this case, there is no solid point. F of A is not defined. But in each case, regardless of what happens at A, limit of f of x as x approaches A is L, meaning we are interested what happens near an A, not exactly at x equals A. We add the fact that if we take a limit of f of x as x approaches either A or A from the left or A from the right, and we end up with either negative or positive infinity, x equals A is the equation of a VA, short for vertical asymptote. The one-sided limit. A function has a limit at A if the limit of f of x as x approaches A from the left equals L. The limit of f of x as x approaches A from the right is equals L. Therefore, the limit of f of x as x approaches A equals L. It's important to understand A, this is read A from the left side of A. A from the right side of A. Okay, so, and the left and right side of each number is the same as far as the sign. So for example, if you are looking at number 4, the left side and the right side, the left side like negative 3.9, the right side is like 4.1. Both sides are positive. If you're looking at, let's say, negative 4, the left side is like negative 4.1. The right side is like negative 3.9. Very close to negative 4, both of them negative. The only number the left side is negative and the right side is positive is 0, and that's when we are going to be careful as we move on with this concept. Example 1, finding limits by numerical and graphical method, and I'm going to add the analytical or algebraic method as well. Guess the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. Notice f of x equals x minus 1 over x squared minus 1. This expression is not even defined when x equals 1. Does it matter? Well, no, because we are not saying what's the value at x equals 1, but rather as x approaches 1 when we get closer and closer to 1. So the numerical method says, let's evaluate f of x, however many decimals, for values of x that approach 1 but are not equal to 1. Well, we are going to make up tables. The tables below give values of f of x for values of x less than 1 and x larger than 1. Okay, so x less than 1, 0.5, 0.9, 0.99, and so forth. Please understand, even 0.9 is way too far. So the more nines you add after the decimal, the closer you are. And so plugin gives you this table. For x larger than 1, these are some numbers. Even 1.1 is way too far. So you put 1 point, a bunch of zeros, and then 1. And now put it into this, gives you that. And as you can see, This number is closest to 1 among those from the left. This number is closest to 1 from the right among those numbers. So if you look at this last row, there seems to be the answer here for 0.9999 and this answer for 1.0001. And if it's not good enough to tell you the limit is 0.5, then add more nines here, add more zeros before 1, evaluate this numerical method. And that's why numerical method may be used, but analytical method is more important. Graphically, if you were to graph this, when x approaches 1 from the left and x approaches 1 from the right, both of them are moving towards this hole. There's a hole here, and this hole has a y coordinate 0.5. Bear in mind, we are not interested at 1, but rather close to 1. However, what is the algebraic method? And what happens when you plug in, you get 0 over 0. As you recall, 0 over 0 is indeterminate. And if you recall, we said indeterminate means more work, meaning use your algebraic techniques, in which case we are going to use the conjugate. A squared minus b squared is a minus b times a plus b, and we notice the denominator is x squared minus 1 squared, and it can be factored into x minus 1, x plus 1, dropping the common factor of x minus 1 gives us 1 in the numerator, and plugging in we get 1/2. And as you can see, numerical method gives us 0.5 or 1/2. Graphical method gives us 0.5 or 1/2. Algebraic method gives us the same answer. So 3 different methods prove the answer is the same, 0, 0.5, or 1/2. All right, one-sided limit. Let's look at this function. The function h is defined by h of t equals 0 if t is less than 0 and 1 if t is larger than or equal to 0. This is a piecewise defined function, everybody. So when we say the limit of h of t as t approaches 0 from the right equals 1, the symbol x approaches a from the right means that we consider only x larger than a, limit of f of x, as x approaches a from the right. So you look at larger, and it's a constant 1, so the limit is the same thing. On the other hand, the limit of h of t as t approaches 0 from the left equal to 0, the symbol x approaches a from the left means that we consider only x less than a, limit of f of x, as x approaches a from the left. So you look at less than, gives you this branch, it's a constant 0, that's the answer. And the limit is, the limit exists if one-sided limits are identical. Since the two are different, the limit of h of t as t approaches 0 does not exist. Notice, by the way, h of 0 equals 1 because the meaning of equality gives rise to the functional value. At t equal to 0, h of 0 becomes 1. Also, if we were to graph this, okay, notice that h of t equals 0, the x-axis, or now the t-axis, and it's for t less than 0. It's good all the way to here, and there's a hole here because we have no equality. On the other hand, h of t equals 1 for t greater than or equal to 0, or y equals 0. It's the horizontal line, and it starts from precisely 0. So because we have the equality, so we have a solid point and then the half line here. And so, one-sided limits. A function has a limit at a if the limit of f of x as x approaches a from the left equals L, and limit of f of x as x approaches a from the right is L. Therefore, the limit of f of x equals L when x approaches a. So, one-sided limits must be identical. Given the graph, example 2, given the graph of a function g, state the values, if they exist, of the following. We are interested in finding the limit of g of x as x approaches 2, and therefore we are going to look at one-sided limits. The limit of g of x as x approaches 2 from the left means we move towards 2 from the left along the x-axis. When we do that, it puts us in this branch, moving towards this point, having y coordinate equals 3. Limit of g of x as x approaches 2 from the right, like so. As we approach 2 from the right along the x-axis, puts us in this branch. We are moving towards this hole, having y coordinate equals 1. And because the one-sided limits are different, the limit of g of x as x approaches 2 does not exist. We are interested in limit of g of x as x approaches number 5. And again, we're going to look at one-sided limits. So we are going to look at number 5, approaching it from the left, meaning coming this way. From the right, meaning coming this way. And whether we approach the 5 from the left or right makes no difference. Left and right, both of us, is moving, both of them are moving towards this point, having the y coordinate equals 2. Because the two are identical, the limit of g of x as x approaches 5 is also 2. However, notice the g over 5. If you look at the solid point, solid dot, as a y coordinate of 1.4, that means g of 5 is almost that. Well, it's close, it's not exactly 1.4, which is not equal to the limit, which means it is still discontinuous. The function is discontinuous at x equals 2. The function is also discontinuous at 5 because the functional value is different. And what makes it even worse at g of 2 is that at number 2, because g of 2 is not even known, we don't have a solid point. So also g of 2 is undefined. It's not given to us. So a quick recap. When x approaches 2 from the left, we are moving towards this point, gives us 3. From the right, we are moving this way, gives us 1. The two are different, the limit doesn't exist. However, as we approach 5 from the left and right, both of them gives us this point. We are moving towards this point, resulting in number 2. The difference is that the g of 5 is defined to be this number, roughly 1.4. Again, since it's not equal to 2, it's discontinuous. But g of 2 is not even given to us because there is no solid point. The graph is given, and we are going to find the limit of f of x as x approaches 2. That's why we look at limit of f of x as x approaches 2 from the left and right, one-sided limits. So from the left, we move towards this point, which has a y-coordinate 3. From the right of number 2, we are moving here, which gives us the y-coordinate. We're moving towards this hole, which gives us the y-coordinate of 1. Are these two identical? No. Therefore, the limit of f of x as x approaches 2 does not exist. These two must be the same, and they are not. So what is f of 2? You look for a solid point here. This one is a solid point. So f of 2 is the y-coordinate of this solid point, which is 3. The limit of f of x as x approaches 4. So as we approach 4 from the left, as well as the right, in both cases, we are moving towards this point from the left or from the right. Both of them gives us this point. We never get there, but the y-coordinate of that is 4, and so the answer is 4. The limit of f of x as x approaches 4. Please understand the concept of a limit. We never get there. However, what is f of 4? That means precisely at 4, what do we have? Nothing is given to us. We don't know. It's undefined. It's undefined. Infinite limits. This definition is illustrated graphically in following figures. So if you look at this figure, the limit of f of x as x approaches a from both sides, it goes to infinity. At the bottom one goes to negative infinity. Same thing, similar definitions can be given for the one-sided infinite limits. Notice, in this case, the limit of f of x as x approaches a from the left side goes to infinity, whereas here from the right side, the limit of f of x as x approaches a from the right is infinity. In this case, the limit of f of x as x approaches a from the left is negative infinity. In this case, the limit of f of x as x approaches a from the right is negative infinity. And all of these tell us this vertical asymptote or VA story that x equals a is the vertical asymptote, because if the limit of f of x as x approaches a, or a from the left or a from the right gets to negative or positive infinity, then x equals a by definition becomes a vertical asymptote. A simple example, we all remember the natural log. Y equals ln x. Of course, all basic logs, the domain is 0 to infinity, and for all logs, basic logs, that means, for example, log x with any base in 5 to name it. The y-axis is the VA, the limit of ln x as x approaches 0 from the right is negative infinity. So the y-axis, also known as x equals 0. So this is limit of ln x as x approaches 0 from the right is negative infinity, and it makes vertical asymptote x equals 0. Pretty straightforward, everybody. So with that being the case, let's look at this graph. Again, reminding you of the definition of a VA. We want to find the limit of the function r of x as x approaches 2. So whether we approach 2 from the left or from the right, in both cases, seems that it approaches negative infinity. Limit of r of x as x approaches 5, whether we approach 5 from the left or from the right, seems to me it blows up to positive infinity. Limit of r of x as x approaches negative 3 from the left. As we approach negative 3 from the left, it goes down to negative infinity. However, as we approach the limit of r of x, as we approach x approaching negative 3 from the right, we approach positive infinity. All of them give definition of a vertical asymptote according to this, so that x equals 2 from here, x equals 5 from here, x equals minus 3, also x equals minus 3. Those are the vertical asymptotes. X equals 2, x equals 5. These two mean the same thing. So these are vertical asymptotes, and vertical asymptotes are not solid lines because they are not part of the graph. Rather, they help us graph functions. Find the following limits. The first approach is to plug in. If you plug in 0, you get 4. Square root of that is 2, minus 2 is 0 over 0, so you get 0 over 0. And again, I remind you, 0 over 0, infinity over infinity, infinity minus infinity, and so on are known as indeterminate forms. Which means more work, which means use your algebraic technique. And because it involves a square root, the algebraic technique is to multiply by the conjugate and divide by it. Please understand, you change this negative to plus, it becomes the conjugate. And the reason you multiply and divide, because this fraction equals 1 and it's acceptable. So we use the fact that a minus b times a plus b is a squared minus b squared. And the numerator becomes square root of x plus 4 squared minus 2 squared, which this comes out as x squared, as x plus 4, and this comes out as minus 4. However, the denominator class, you always keep it the way it is, x times that, and you don't distribute, because when you get 0 over 0, it's 0 in the denominator that creates a problem. In this case, x is creating a problem, which means you are hoping with this process you get rid of it. So for the denominator, you keep it as a product of x, and the square root of x plus 4 plus 2 inside the parentheses. 4 and minus 4 cancel each other. X and X cancel each other. And now if you plug in 0, becomes square root of 4, which is 2 and 2, 4. So 1 over 4 is your final answer. I like to look at these two questions simultaneously. First and foremost, if you ignore the negative 3 from the right and left, I want you to see that if you plug in negative 3, you get negative 1 over 0. And the same thing here, negative 1 over 0. When you divide any number by 0, we used to say it's undefined. Now we say it's either infinity or negative infinity, and you need to figure out whether it's positive or negative infinity. Any number, both sides have the same sign, positive, both sides are positive. For example, number 5, left side and right side. For example, left side is, I don't know, like 4.9, right side is 5.1. If you have negative 4, left side is negative 4.1, which is negative, and right side is negative 3.9, negative. The only number that is different is 0. The left side is negative, the right side is positive. And since the denominator is 0, it makes a difference. When you plug this one into the denominator, negative 3, the right side, let's say negative 2 or negative 2.9. So negative 2.9 plus 3 is 0.1. And so this becomes positive. And so you know the answer is infinity, but negative over positive gives you negative infinity. Whereas this one, negative 3 from the left, like negative 4 or negative 3.1. So if I plug in negative 3.1 plus 3, I get negative 0.1. So this is negative, and that's really the idea. So both of them are infinity, but this one, negative over positive, is negative infinity. This one, negative over negative, is positive infinity. So again, when the 0 is in the denominator, you must figure out if it's from the left or right for the sake of finding the sign of infinity. If it's negative, as is the case up here, or it's positive, as is the case for number 30. As I mentioned, the numerator really doesn't make any difference if it's negative 3 from the right or left, both of them. The numerator is very close to negative 1. As it happens here, if you ignore the 5 from the left, we want the limit of e to the power of x over x minus 5 cubed. That's x approaches 5 from the left. If you ignore 5 from the left, the top is e to the power of 5, and the bottom is 0. That means 0 cubed, which is 0. However, we can't ignore that, because if you divide a number by 0, it ends up being infinity or negative infinity. You need to know the sign. And to do so, the numerator, 5 from the left, like 4.9999. So e to the power of 5 or e to the power of 4.9 makes no difference. What happens is that for the denominator, for example, if I put 5 from the left, 4.9, you can even put 4 because you want the sign. Minus 5 is negative 0.1. I'm interested in that negative. You can say negative 1. This is how you find the sign, negative. So this is 0 from the left cubed. And we know that if you have a negative number and you raise it to the power of even versus odd, makes a difference. For example, if I said negative 3 and I want to raise it to the power of 2, I get positive 9, but negative 3. And I want to raise it to the power of odd, such as cube, I get negative 27. So the bottom line is, because this is odd, the bottom is 0 from the left, and this is infinity. 0 from the left makes a negative, so it's negative infinity. To explain this further, I'm going to get the same question, and I'm going to change this exponent to some other exponent. However, this is odd, this is even. So we have the same thing with the even power of 4. Same thing with the even power of 4. Okay. And so we know with the power of 4, even this becomes positive. And therefore, this is positive infinity. That's the key. Positive infinity. So we want to pay attention when the bottom is 0. We also want to pay attention to the exponent if it's being raised to a power, whether it's odd or even, and the effect that it has. Again, it's pretty straightforward, everybody. And I hope everybody's okay with that, and we're going to take it from there. We want to look at this example. And if you plug in class, you do get 0 over 0, although anytime you are dealing with a fraction, a rational expression, it's really a very good idea to factor it in the first place, okay? But in case, if you don't do that, you get 0 over 0, which is indeterminate, which means you have to do your techniques. In this case, the technique is factoring. And what I want to explain is, first of all, reminding you of the following identities. A squared minus 2ab plus b squared is a minus b quantity squared. A squared plus 2ab plus b squared is a plus b quantity squared. And this is in this format. The first one being squared, the second one, and this is the product of those two times negative 2. So it looks like that. However, if you look at the fact that x is approaching 2 from the left, of course, and it gives you 0, it's important to pay attention to the following. If x approaches 2, you should have a factor of x minus 2. If x approaches 5, you should have a factor of x minus 5. If x is approaching minus 4, you should have a factor of x plus 4. When you factor, the reason I mention it, it will help you with the factoring. Needless to say, the top x comes out and it becomes x times x minus 3. Very straightforward, very simple. The bottom is x minus 3 squared. As I mentioned right here, we can drop the common factor. X minus 2 is in common, and this one drops. And now what happens? If you plug in the 2, you get 2 over 0. And remember, 2 from the left or right, for the top doesn't make any difference. From the left is like 1.999999, almost 2. From the right is 2.000001, almost 2, makes no difference. But the bottom that becomes 0, when you divide a number by 0, it's either infinity or negative infinity. You need to figure it out. So now 2 from the left, we are going to go with 1.9. Even you can go with 1 if you want to show that. So this one If we go with 1.9 minus 2, we get negative 0.1, which results in 2 over 0 from the left. And that is negative infinity. That's the final answer.